Welcome to BAM TV episode 4. My name's Phil Zito. I'm the owner of Building Automation Monthly, and I am going to be taking you through in this week's episode Building Automation Optimization Strategies Part 2. So in last week's episode, or depending on when you're watching this, the previous episode, went through the 5-step optimization process, talked about how retro commissioning is different than optimization, and talked about the upstream and downstream effects of optimization. If you haven't watched that episode, really encourage you to check that out because it's going to have a lot of information that you need to have in order to really appreciate what we're going through in this episode. So in this episode, we are going to talk through the top 5 optimization strategies that I've seen implemented out in the field as part of building automation optimization. So the first thing we need to get really clear on, and I'm going to draw this because I've talked about this in the past in my podcast episodes, and I've talked about it in previous BAM TV episodes, but just in case you haven't seen it, is called the process loop. And this is going to be really important in order for us to properly cover our optimization strategies. So in a process loop, you have a controller, okay? And a controller being a BAS field controller. And that is going to have an output. Let's just say that this is a valve, an automated valve, okay? So it's got an actuator driving the valve. And then on the input, let's say that we have a temperature sensor, okay? Maybe it's a discharge air temperature sensor. Well, what happens in the process loop is inside the controller, it compares this temperature, also known as process variable, to its set point, what it's supposed to be controlling to. And between these two values, it generates what's called an error, okay? So the error exists inside this controller, and then that error drives the output, okay? So in order for us to do any form of optimization, we first have to retro commission these devices, meaning we have to ensure that our inputs are accurate. How do we make sure our inputs are accurate? We do that by going and making sure they're calibrated. You can get simple calibration kits for temperature sensors, for CO2, for CO, for humidity, a variety of different values. You can calibrate flow, you can calibrate pressure, you can calibrate all of your sensors. And it's really important that we calibrate across the full range, okay? For both inputs that we're going to calibrate as well as for outputs that we're going to calibrate. So once you've got your inputs calibrated, then you need to calibrate your outputs. You need to make sure that if it's a actuator sitting on a valve stem, that it is properly set or seated on the valve stem so that when it's at 0% on the actuator, that is a true 0%. We want to make sure that we check those out. So actuators, fan commands, damper commands, etc. We want to make sure that our outputs are properly controlling. If these two things aren't done, you can optimize till you're blue in the face. None of that stuff's going to matter because you're going to be driving off of inaccurate settings. So for example, our first optimization strategy is supply air temp set point reset based on load. Now typically it's an air handler, and this air handler has a discharge air temp or supply air temp, depending on what you want to call it. And it'll have, maybe we'll give it a cooling coil, okay? And what happens is downstream, either there's a space or maybe there's multiple spaces. And what this sequence, what this optimization strategy's purpose is to reset this discharge air. And the purpose around resetting the discharge air is that upstream of this cooling coil is your central utility plant. If we go and we back up our discharge air temperature set point, meaning we increase it maybe from 55 to 65, what happens is that makes the coil less likely to open. When the coil is less likely to open, that means that there's less pump energy required. That means that the cooling to provide to that secondary loop or primary loop is lowered, so it has upstream effects as well as just reducing the wear and tear on the equipment of the air handler. But how do we determine what we're going to do? Well, first off, remember how I said we have to go and have accurate inputs and outputs. Now you're seeing why these are so accurate. If we're not properly measuring supply air temp or the other variables that I'm about to get into, then we are not going to be able to control. So what we're going to do is we typically have a couple different variables that we can reset off of. We can do outdoor air temp, we can do space temp, and then we can do damper position. Okay? So what we can do with these three variables, and these are kind of in the order of what I would recommend. And also when we say space temp, we could also kind of throw in there RAT, return air temp. Now, outdoor air temp, in my professional opinion, based on my experience, is the worst way to reset almost anything. Outdoor air temp does not account for actual load in the spaces. And when I say load, I'm talking either the heating that is required or the cooling that is required. So either the removal or addition of BTUs into the space, all right? Or out of the space in the case of removal. So outdoor air temp is the least ideal method for us because it doesn't take into account the localized load. It just takes into account what the dry bulb temperature is within a specific area. And that area may not even reflect what the accurate outdoor air temperature is. So that's really important for us to be aware of. After that, then, so we've got outdoor air temp, we've got space temp. This is where, so we've got, in this case, space 1 and space 2. And with space 1, what we want to do is, if it's a single space, then we just look at the space temp and the difference between space temp and set point. And so that difference, once again, between space temp and set point is error. And we have an error, and we would say maybe 0 to 4 equals 10 to 0. And you're like, what the heck does this mean? This is a span block, okay? This is commonly used in programming, and we're going to use it throughout these different optimization strategies. So 0 being our error, so this is our error, and this is our set point adjust, okay? And so what we're going to do is, as our error gets lower, we are actually going to go and raise the discharge air temp. So we would take maybe 55 degrees and add 10 to it. But if we have a 4 degree or greater error, then we go and have our regular 55 degree discharge air. Like I said, I don't necessarily recommend on using space temp or return air temp because there could be other factors that are leading to that issue. What I like to do is drive it off of damper position. Damper position is a value that allows you to look at, hey, this damper is 100% and I am still not cooling down the space. That's a lot different than the damper's at 40% and I'm not cooling down the space. That is indicating a different issue, most likely a PID tuning issue. But 100% and not cooling down the space, as long as that damper's reliable, which, by the way, let me draw this over here for those of you who don't know what I mean by damper being reliable. So on a box, typically, right, you've got your air coming in here, you've got your actuator, you've got your flow sensor, so this is your DP, and this is coming from the AHU. And then it goes into the box and then goes out to your diffuser, okay? So you got your airflow coming through, and then this damper opens and closes to control to a certain CFM, all right? Well, if a damper is 100% and you've got 0 or 10 CFM, that's a reliability issue, and then you would throw out the damper position. You wouldn't utilize the damper position. If you have 100% and you have the right flow, then that indicates either a cooling capacity issue or a missized space. However, still, using damper position, in my opinion, has been more reliable than using space temp. I know folks who swear by space temp error, looking at space temp versus space temp set point for resets, and I know folks who swear by damper position. Honestly, either one is fairly accurate. It just depends on what you feel most comfortable using. I find that damper position, when a box is properly configured, is more reliable because temp sensors tend to drift and the airflow tends to stay the same longer from my experience. But either one, you're not going to go wrong. Avoid outdoor air temp if possible. All right, so that is strategy number 1. Strategy number 2 is hydronic set point reset based on load. So let's clean off the board and then we're going to go through that. Okay, so hydronic set point based on load. What we mean by that, and we're just going to use a chiller for this example, an air-cooled chiller. So you have your chiller, right? And coming out of this chiller is a pipe that is going to a coil. Okay, so we're going to have a coil here. And this is not reflective of a mechanical drawing. So don't be concerned about valve positions and coils and all that. I just want to talk through kind of what's going on here. Okay, so a two-way valve right there going to a loop on a chiller. Okay, so what we're looking at here is we've got a chiller, we've got a two-way valve, we've got a coil, and what we want to look at when we're doing a reset on load is one of 3 things. We're going to look at OAT, we're going to look at valve position, or we're going to look at BTU. So any of these 3 can reset the supply temperature set point. And the theory, once again, very similar to the air handler, is that we go starting off at 42 degrees and we can go up to 52 degrees. So we have a 0 to 10 span based on load. So what a lot of folks will do is they'll just do purely outdoor air. As outdoor air starts to climb, they go and increase the chilled water supply set point. Now, that is not ideal, especially with a lot of chillers that don't have variable speed compressors, or especially air-cooled chillers. It's not ideal to go and just sit there and keep something at 42 degrees even though there's no load in the building, because at partial load conditions the chillers aren't as efficient. Some of them are if they have variable compressors and a variety of things like that, but in a general perspective, it's better to base your reset off of one of these scenarios. Valve position, so average valve position, if all your valves are open, that indicates that your coils are flowing water through them because your coils are needing to have chilled water. So as you reach above a certain position, you would basically use a comparator block, and you would take, average valve, and then you would say, maybe we want to say 70%. So if our average valve is greater than 70%, then we send through a increase in temperature. And how we would do that is you would use what's called essentially a, what's the word I'm looking for here? think it's trim and response, which is a sequence we're going to go through. Basically, you're adding to it over time. So that is a time perspective. You can do that. Or you can simply do a reset. You can have average valve, and that can be 0 and then 100, and then you reset from 10 to 0. And that is in addition, so this is an upwards reset right here. You reset your chilled water supply temp set point, and you're adding. So you add 10 when you're at valve 0, and your range would probably be a little broader. And then finally, BTU is where you take delta T, so you take your temperature sensor, your temperature difference between supply and return, that's your delta T, so return minus supply, times your flow, times I think 500 if I remember correctly. That's your BTU calculation. And then you convert your BTUs to tons, which I don't remember the calculation off the top of my head, but you can go to engineertoolbox.com or just Google BTU to ton, and there's a calculator right there. There's no reason to memorize this stuff anymore, folks, because with your phone or just with your computer, you can easily go and find the answer. So once you've done that, what you're going to do is you're going to go and say, hey, I've got my BTUs. I've converted that to tons of cooling. And then you're going to look at your chiller, and you can actually go and say, hey, this chiller's rated for so many tons. I'm going to increase or decrease the set point. I tend to most of the time use the average valve position because it's what most folks know, and they get a little uncomfortable when they have to calculate BTUs and convert it to tons. However, if you're ever going to do chiller staging, that BTU is really nice for staging up, especially if you have a partial load chiller. But it's also really nice for resetting set point as well. Okay, so let's clear this off, and then let's go through trim and response based on demand, which is an airside strategy for pressurization control. All right, trim and response. So we're going to pick up the pace a little bit on this video because this is starting to get a little long, and want to make sure that we get you all through this in a reasonable amount of time. So trim and response based on demand is looking at the same demand factors that we've seen in the past, which could be space temp, could be, we could say damper position, we could say airflow, air. These are kind of the main areas, but the main one is going to be damper position. And essentially what is happening is we're taking the damper position from a bunch of VAV boxes, and we're sending that to a central controller that is then averaging or doing a high select of these VAV boxes and saying if DPR, damper position, is greater than set point for maybe 120 seconds, then we increase by maybe 0.2 our discharge air pressure set point. And so, whereas our previous strategy with the air handler was focused on resetting temperature, here our strategy is focused on resetting the discharge air pressure set point. So the temperature, the theory behind temperature reset was that by increasing the temperature, the coil would have to open less. The theory here is that where you can't necessarily do temperature reset, what you can do is you can reset pressure, because less flow going through the coil means less BTUs being transferred to air, which thus is less demand both on the actual fan as well as on the coils. So that is how you're going to go and implement trim and response. You're going to use one of these, and then if it's above that set point for a certain amount of time, you go and you increase the pressure set point. If it is actually below, so here would be set point, and here would be DPR POS. Once again, and it's below it for 2 seconds, or for 2 minutes rather, then we would subtract 0.2. And that would be DAP-SP. And then both of these right here would go into a limiter that limits the high and the low so that these don't go and cause an issue. Although you could also go and just say that, hey, I'm going to disable this when the set point, calculated set point, drops below a certain discharge air pressure set point value. Okay, so let's clear this off, and then we're going to go through economizer operation, which is everyone's kind of favorite area. So economizer operation, what is an economizer? Well, an economizer, quite simply, is a part of a rooftop unit or an outdoor air unit that opens up to allow outdoor air in. And there's really 3 ways we can optimize our economizer. We can optimize our economizer to control DAT. We can optimize our economizer to control MAT, or we can optimize our economizer to control CO2. Okay, so when we're controlling discharge air temp, basically what we're doing is we're maintaining, maybe 55 degrees. And then when we're controlling mixed air temp, we may be controlling, 52 degrees because we're going to have a little bit of heat gain before we get there. And then CO2, we're controlling to maybe like 800 to 1,000 parts per million. So all of these right here will end up controlling the min position. Notice I said min position of the economizer. And these will be using PID loops. Now, how do you go and enable economizer? That's another optimization strategy. So a lot of folks will just do OAT dry bulb. Dry bulb meaning it's not factoring in the moisture content of the air, it's just the air temperature. It's kind of what you see if you were to look at your phone and see air temperature. So you've got that right there. The other way is to compare OAT to RAT. While not necessarily the best way, it still is a little bit better than OAT only, because now you're looking at return air temp and you're saying, hey, if return air temp is less, then we're going to use mainly our return air damper and not our outdoor air damper. The ultimate way is to use what's called enthalpy. Now, I'm going to draw a really bad drawing of a psychrometric chart. So essentially, a psychrometric chart looks something like this, and you have dry bulb temperatures, these vertical lines, and then wet bulb temperatures, these kind of horizontal lines, and then humidity, relative humidity, are these lines that are kind of going along here. Well, if you follow dry bulb temperature across, you have the amount of moisture that is in the air, and that's measured in grains per pound, if I remember correctly. And what happens is at warmer temperatures, so this is like cold and this is hot. So at warmer temperatures, you have more moisture in the air at the same relative humidity. So if this is like 90% RH, then here at 90% RH, you have a lot more humidity or moisture in the air than down here. Well, enthalpy control looks at the amount of moisture in the air because moisture contains energy. And in order for you to go and realize if you have to use your cooling coil to remove a lot of that moisture and energy, you look at enthalpy. So if the enthalpy of outdoor air is lower than the enthalpy of return air, even though return air dry bulb may be higher than outdoor air dry bulb, there's actually more energy in the outdoor air that needs to be removed. So that is kind of the golden standard way of enabling economizer. And these are kind of the three modes for controlling economizer. And in the last optimization strategy, we'll talk about optimal discharge or differential pressure sensor placement. All right, so for the fifth strategy, and this is not so much of an optimization strategy as it is more just of an experience strategy, something picked up over the years I've seen a lot of people make mistakes on, and it's called optimal DP sensor placement. So let's say that you have a air-cooled chiller here. The general rule of thumb is that you're going to have kind of your DP sensor down here, down from here, and once again, these drawings do not reflect how it would actually look in the field. So just forgive me for that. I'm not actually going through here and taking the time to reflect how the coils and valves would be placed, because that's not what we're focused on here. We're focused on DP. I see a lot of folks putting the differential pressure sensor here, and you got a pump and it's hitting differential pressure sensor right here, and it's overpowering that sensor, and so you get this pump this pump control that looks like this instead of more like this. So that would be 100 and 0. So instead, you should have something that looks kind of smooth, not these peaks and valleys. And that's why you want to move the differential pressure down here, so that you will go and have better control, because you're actually giving the pump time to push water to both of these coils. And in a plant, there would actually be a lot more coils. But you're giving a pump time to actually fill the loop with water at the right pressure, and thus meet differential pressure, versus meeting differential pressure immediately and causing the pump to cycle up, down, up, down. So this is kind of a tip. If you run into plants or air handlers that the fan or the pump, or the pump or the fan rather, plants and air handlers, the pump or the fan are ramping up and down, then it's most likely that your differential pressure sensor is too close to those devices. All right, so that is it for this episode. I know this episode went a little bit longer than normal. Thanks for being here. And in the next episode, we're going to be diving into something. I just haven't figured out what it's going to be yet. I've got a couple different ideas. Maybe dive into some more programming. Maybe dive into some system integration or IT. That's up to you. Why don't you leave me a comment in the comment section below? Let me know what you'd like us to cover in BAM TV episode 5. And who knows, maybe what you suggest will get picked. Thanks a ton, and I'll see you all in the next episode. Take care.